Hello everyone, my name is Kirsten Hazler, and I'm a landscape ecologist with the Virginia Natural Heritage Program. Today I'm going to give you an overview of a prioritization model we've developed to help maintain healthy waters in Virginia. The Healthy Waters Program is jointly housed between the Virginia Natural Heritage Program at DCR and the Center for Environmental Studies at VCU. Through the Healthy Waters Program, stream reaches are sampled and stream health is quantified using a variety of biological and physical metrics. The stream reaches are then classified into 4 categories. So you see the outstanding reaches are marked in green, healthy reaches marked in yellow, restoration candidates marked in blue, and compromised reaches marked in orange. And when I say healthy waters, I'm actually referring to the reaches that are in the top 2 categories, so either designated healthy or outstanding. And as you can see in this map, most of the samples are in the Chesapeake Bay watershed, but eventually we should have more samples that better cover the state as a whole. The Chesapeake Bay program has a number of different goal implementation teams, GIT for short. One of these is the Maintain Healthy Watersheds GIT. This group seeks to ensure that 100% of state-identified, currently healthy waters and watersheds remain healthy. The idea is that it's more cost-effective to keep healthy streams healthy rather than to have to restore and clean them up later. Now, every state has their own definition of what healthy waters are. Here in Virginia, they're defined by our Healthy Waters program, as I went over in the last slide. The watersheds draining to the designated healthy waters are called healthy watersheds. As I'm sure everyone here is aware, what happens on the land impacts the health of our streams by way of non-point source pollution. But any given activity, such as cutting down a forest, for example, can have more or less impact depending on where in the watershed it occurs. So given the fact that we don't have unlimited resources for land protection and for implementation of best management practices, we need to apply an approach that's going to prioritize protection of the most critical lands needed to protect water quality at the source. So this model is trying to do several things. We want to identify the lands most important specifically for protecting Virginia's healthy waters. We want to prioritize areas on the land where activities are likely to have the greatest impact on aquatic resources. The impacts could be positive or negative. And we hope this model can be used then to help target lands for conservation and for implementation of best management practices at landscape scales. Before I proceed with explaining the model, I wanted to acknowledge some of the resources that were especially influential in model development. The Open Inspect software was developed by NOAA, and it's intended to look at different potential land use scenarios within a watershed and to estimate the effect of land use change on pollutant loads reaching streams. The software itself didn't quite meet my needs, but the technical documentation had a lot of really great information and concepts and equations and coefficients that I was able to build into our model. And then this paper over here by Barton and Ernst describes a prioritization model for protecting drinking water sources, and they had a lot of ideas that I incorporated, probably the most influential one being that they generated separate priorities for conservation and restoration and urban stormwater management, which I also incorporated into our model. The Healthy Waters prioritization model is really just an adaptation of the Conservation Vision Watershed Protection Model, which we plan to complete this year. It's still in draft. We're definitely still open to comments and feedback to help make it better. But this slide gives you a general overview of the model structure. Over here, we've got the potential impact component. That's intended to identify where on the ground an activity is expected to have the greatest impact on waters downstream. Here I'm talking about any waters, not just the designated healthy ones. And that depends on both on properties of the soil as well as the position in the landscape. Over on the other side here, we've got an importance component. And that indicates the relative importance of an area relative to specific resources of concern. So this is more human values driven. You could insert anything of interest here depending on your focus. For example, if you're focused on drinking water, your resources of concern could be the specific locations from which drinking water is sourced. In our case, though, we are looking to maintain healthy waters in a healthy state, and so the resources of concern for us are those stream reaches that have been identified as healthy. So then we put together the importance and the potential impact components to come up with an overall priority value, and then those priorities are further split up depending on land cover. So if you have a forest or other natural type vegetation, that's going to be an area where you have a conservation priority. If the land is already developed, it's not going to be for conservation, but it could be a focus for stormwater management. If it's rural lands, the focus might be to implement agricultural best management practices, or maybe even to restore some vegetation back to a more natural state. So in the upcoming slides, I'm going to go over these various model components in a little bit more detail. Try to keep this overall structure in mind as I go through it. So first, I'm going to talk about relative importance. Here, the relative importance of a location on the land depends on where it is in relation to known healthy water stream reaches. Now in this slide, you can see right here, this yellow star indicates a known healthy water site. And its full watershed is shown here in the pale yellow. And we also delineated truncated watersheds that were limited to 2, 3, 5, or 10 kilometers upstream of the point. And you can see these in different colors in this inset enlarged map. So we make the assumption that areas closer to the healthy water site are more important than areas farther away. And when I say closer, I mean hydrologically closer, as the water flows, not as the crow flies. If a place on land doesn't actually drain to a healthy water site, then from this model's perspective, it's not important. Now this slide, this shows the exact same location we were just looking at. Here's that same healthy water site. But now you can see that in addition to that one site, there are multiple other healthy water sites in the general area as well. And you can see that some areas drain to multiple healthy water sites. So we delineated both full and truncated watersheds for every single healthy water site, and many of those watersheds overlap. So we literally counted the overlaps and converted the counts to importance scores that could range up to 100. This is all based on the assumption that catchments contributing to multiple healthy water sites at multiple scales are more important than those contributing to a single site at a single scale. Okay, so we have covered the importance part of the model, and I just wanted to also mention that importance is limited by the sampling effort. Only documented healthy sites actually contribute to the score. Now certainly there are some stream reaches that are healthy but not documented yet because they haven't been sampled or analyzed. These didn't make it into the model. We're focusing right now just on maintaining what we know to be healthy. Over time, as we have more samples across the state, this will definitely change. Next, I'm going to talk about the potential impact side of the model. This slide gives an overview of how potential impact is determined. So it's determined based on a number of different factors. So first off, we have equations and coefficients that we got from the Open Inspect program, as I mentioned earlier. Precipitation, the type of soil, how steep the slope is, how far the water flows across the land before reaching streams, and the prevalence of karst in the landscape. So fundamentally, potential impact depends on what I'm calling soil sensitivity, which is based on runoff potential and soil loss potential on the one side, and then it's also based on landscape position, which is based on the flow of water across the land, as well as the prevalence of karst in the landscape. So I'm going to go through each of these subcomponents in turn. One aspect of soil sensitivity is the potential for rain runoff. The more runoff there is, the more pollutants can be carried from the land to the streams. Runoff potential depends both on the amount of precipitation as well as something called a runoff curve number. And the runoff curve number itself is based on both the soil type, namely the hydrologic group, as well as the land cover. And for this model, instead of using the actual land cover, we assumed barren land. This basically gives us a curve number under a worst case scenario. I wanted a soil sensitivity measure that was independent of the actual land cover. That's why I did that. And then for precipitation, you also have to choose a particular scenario to come up with a value. So I chose the DCR Dam Safety's probable maximum precipitation tool and assumed a storm duration of 24 hours to come up with a precipitation value. So once you have a precipitation value and a runoff curve number, you can plug these values into the SCS runoff equation and you come up with an estimated runoff volume. And this runoff volume was then rescaled to a score ranging up to 100. So I'm not trying to estimate the actual amount of runoff, but rather a relative measure of the potential for runoff under extreme conditions. The second aspect of soil sensitivity is the potential for soil loss. The more soil is lost from a piece of land, the more sediment ends up in the streams, along with any pollutants that were carried by that soil. So to measure potential soil loss, we used 4 factors of the revised universal soil loss equation. So we have an R factor that measures this rainfall erosivity factor, and we got that directly from the OpenInspect website. There's a K factor, which measures the erodibility of the soil. We got that from the GSurgo soils database. There's an S factor that depends on the steepness of the slope, and that's derived from a digital elevation model. And then there's a C factor, which is a cover management factor, depends on the type of land cover. And again, I went with kind of a worst case scenario and assumed barren land instead of using the actual land cover. And so multiplying these Roosley factors, you come up with a product. That product was rescaled to a score. So a score of 100 would indicate the maximum soil loss. So once again, this is supposed to give us a relative measure of the potential for soil loss instead of an absolute measure. The position on the landscape matters. As you all know, a site that's directly adjacent to a stream is likely to have a much greater impact on aquatic health than a site that's farther away. So we assume that potential impact decreases with increasing distance from a stream. And we measure distance as the water flows, not as the crow flies. So from any given point on the landscape, we can measure the flow path down to the nearest stream, and those flow path lengths were then converted to scores. Again, score maximum would be 100, and that would be right adjacent to water. We also weighted the headwater streams more heavily because of their strong influence on downstream waters. We incorporated this concept in the model simply by slightly discounting scores in non-headwater catchments. Karst landscapes are especially sensitive. Sinkholes can provide a conduit for surface waters and any pollutants that they might carry to directly enter into the groundwater. And the direct connection between surface water and groundwater, combined with really fast and largely unpredictable underground flow patterns, makes groundwater and springs in karst regions especially vulnerable to pollution. So we calculated subscores based on proximity to karst geology as well as the density of sinkholes. And these two subscores were combined into a composite karst score. So here you can see we've derived a soil sensitivity score based on the mean of the scores for runoff and soil loss potential. And on the other side, we've derived a landscape position score based on the greater of two scores, either the overland flow score or the karst score. And finally, the soil sensitivity and landscape position scores are combined. We take the mean of those to come up with a potential impact score. So now we have a potential impact score, we have an importance score, we calculate the product of those two scores, and then we slice that into priority quantiles. So you can say, here's the top 10% most important, or top 20% most. And then those priorities are split by land cover. So if it's forest, like I said, or other natural land cover, it's going to be a priority for conservation, marked in the green shades. Orange shades indicate the best management practices or restoration priorities in rural landscapes. And then the purple indicates the stormwater management priorities for urban landscapes. And the depth of the shade indicates the higher priorities. So you can really see there's certain areas that obviously seem to be worthy of more attention, like up here, over here. These darker areas, darker shaded areas, are going to be areas that this model would indicate we should focus our efforts on. I should emphasize this is a landscape scale model. It's intended for general screening. So once you've used it to identify some target areas, you definitely would still want to get additional, more detailed local information to decide whether and how to proceed. And I also want to mention, although this looks like a single output map, it's actually 3 different maps. There's one for each type of priority. Where I work in the Natural Heritage Program, we're focused on conservation. So the conservation priority map would be of most interest to us. And so you can see here in the darker shades, those are the areas that would be areas to target if we want to try to maintain healthy waters. And I've overlaid that with conserved lands in that kind of tannish color, so you can see that some of those target areas are covered already, they're already conserved, but a lot of them are not. So this would be really informative to areas, to find new areas that we really need to focus on conserving. Other organizations may be more interested in the other 2 maps, either for the urban end of things or the more rural agricultural landscape end of things. And so these can be used to help target areas for implementing best management practices and restoration of natural vegetation. And that is the end of my presentation. Thank you for listening. I'm going to try to take some questions here in the session. If you'd like to reach out after the session at any time with more questions or any feedback on things we might have missed or should improve in the model, please do get in touch. I've got my email there on the slide, so feel free to reach out and be happy to hear from you. Thank you.